calculus lesson on summary of curve sketching. This will be part B. All right, we did the part A earlier. For this one, guys, we have a warm up. So do me a huge favor and try this on your own, and we will go over this in class. Okay, and do not rely on the use of graphing calculator. Try that at the very end. Okay. When I say graphing calculators, that includes any online graphing aid, including Desmos. Okay. All right. Be mindful of the slant and oblique asymptotes. All right, guys. All right. A quick hint: when you take a limit, right, as x goes to infinity of, let's say, the function f of x, and let's say that becomes, I don't know, that becomes like x squared. Remember, that's a function that's equivalent to. So as what that means is as x goes to infinity, it means that the y is behaving as x squared. So the curvature will be quadratic. So it's increasing in a quadratic form. Okay. So that's something that we may not have talked about explicitly, but that's something that you should take into consideration when you're doing all of this, guys. Okay. All right. All right. So I will leave you alone to work on that on your own. And then let's move on with the lessons that we have. So we'll be talking about, this is more like a review. We will be going back to revisit certain techniques that some of you may or may not have learned, right? And I think most of you should have learned this already. And we're going to focus really on the slant and the oblique asymptotes, right? In relation to the rational functions. So when you have polynomial function, rational function made of polynomials, we got n of x being the numerator and d of x being the denominator, divisor, right? And then let the degree of n of x be p and the degree of the denominator be q. If the numerator has a lower thingy, what have you learned, guys? Versus when they're equal to each other. So basically, as x goes to infinity, y goes to 0. And here y goes to the ratio of the leading term, which is 3/4. And then over here, using the technique that we already learned, that's actually 1/3 x. So as I mentioned earlier, if the limit as x goes to infinity is equal to this, it means as x goes to infinity, right, the y behaves like it's 1/3 of the x. So when x goes this way, y rises a third of the height. So it increases linearly. It's going towards the infinity in a very linear fashion, right? So write what you can over here and graph what you can and see what you can do. All right, guys? All right, guys. So assume that you worked on it. If not, pause the video and start it again. And here it is. And this right here, for case number one, if we use the technique that we learned already, you could simply show that we will multiply the both numerator and denominator, multiply the numerator and the denominator with the reciprocal of the leading term of the denominator, right? And that will yield 0 because 2 over x squared is 0, 1 over x to the fourth is 0, so 0 over 3 is 0. Or simply, if you don't want to show this work, and at this point you have the freedom to write it this way. You could say that whether it goes to positive or negative in this case goes to 0 because the polynomial degree of the denominator is greater than the numerator. You could say that. It is now acceptable, okay? Now, using the technique that we just learned in calculus, we would figure that 1 over x squared, and 1 over x squared top and the bottom, we're left with 3 and a 4. So these go to 0, right? Or we could simply say that equal to 3/4 because the ratio of the leading coefficient, the limit is the ratio of the leading coefficient because the degree of the polynomial is equal for numerator and denominator. Okay. All right, the last one. So we have this, and I just did a long division. That's all I did, right? You don't have to multiply by 1 over x, right? You could, if the denominator is a monomial, it might be just easier to just do a long division. In fact, it doesn't have to be monomial. And that will be the emphasis of today's lesson, right? So when you do this, this will go to 0, which means that we have this. And as I mentioned before, as x goes to infinity like this, the y will go 1/3 the height, right? So that's how it goes to the infinity. So the ratio, its behavior as y goes to infinity is very linear, right? Now, when I do a long division, I do end up with this, okay? Think about this. As x goes to infinity, this goes to 0. I got the same result over here simply by doing a long division, right? And this is the q of x, the quotient of x, and that is the behavior of the graph. Now let us examine each function. And this one, if you graph it out, looks like this. And we're going to talk about the specifics of why it looks that way. And we'll do the same thing over here. And then what's interesting for us is that the slant asymptote right there, guys, is indeed 1/3 of x, the quotient of x. So that's the note, the big note. For those of you who had me in pre-calc honors, know that I really emphasize this, right? That is the in behavior equation. I don't know what a good name is. So at some point, it's not a slant asymptote. So I guess this is oblique asymptote, right? Maybe you could think of this as an envelope. The graph goes within that envelope, right? Right. So yeah, there it is. So we have something similar. Not this is x squared over x. We have, in this case, x cubed over 2x plus 1. So I mentioned that you could do a long division, right? Why don't you guys go ahead and try this on your own first and see what it looks like. Okay. I'm going to assume that you did that already. And here, clearly, my x-intercept is what? Set the y equal to 0 is a 0, right? Well, what is my x-intercept? That is also 0. So it goes through 0, 0, obviously, right? And then we talk about the vertical asymptotes. Now let's talk about the asymptotes right there, right? When we talk about the asymptotes, let's zoom in just a tiny bit. That we talk about the vertical asymptotes first, but vertical asymptote does not exist because x squared plus 1 is never equal to 0. So what happens as the limit as x goes to infinity, right? So you multiply by 1 over x squared, and we'll end up with the limit as in the numerator is just x, that'll be 1 over x squared. Obviously that goes to 0. And we have that the y is this. So what that tells me is that my y value is equivalent to this, its behavior. So as x goes to infinity, my y behaves like x, which also goes to infinity. Oh, it's behaving linearly. Okay. We could do a long division, right? And what we'll find as we push forward is that my graph will go through it like that, right? And what else should we do? We should also study the symmetry, right? Okay, good. All right, guys, I'm going to show you my worked out solution. Here we go. So I did the same thing. I did a long division and I found that q of x is x, which is the in behavior. As the x pulls away, x goes to positive, negative, infinity, my overall graph looks like y equal to x. And clearly as x goes to infinity, like this, it's getting closer and closer here and closer over here, right? Yep, so I talked about that right there. And then I played for p of negative x, which turned out to be an odd function. So as long as we could draw this part, we could draw the other side, right? And then I did the derivative of the p of x and then found that the slope is equal to 0, right? When x equal to 0. So its slope is like this over here, right? And then there's no point at which the slope of the p of x does not exist, right? So I just drew the y value here, number line f prime y. I'm sorry, that should be like p prime, not f. Okay, so it's old habit. So p P prime and P double prime. Okay, and I also do that for the curvature as well. And I think it really wasn't necessary in this case. So let's study this. I just want to focus on this right here. Okay, let's think about that really, really, really carefully. Just think about that carefully. So as x goes to infinity, plug in a gigantic number and see what happens here. Okay, when x is 1,000, we got negative 1,000 over about 1,000,001. That right there is whatever the x is about 1,000th below the x-axis. So even before we began, I already knew that my graph was going to be a tiny bit below. What if I plugged in negative 1,000? Well, the numerator is, then it becomes positive 1,000. Denominator, because it's a square, it'd be 1,000 over 1,000,001. That's approximately a 1,000th above the x. So I know that immediately that I am slightly above x, right there. And I know that my slope was equal to 0 when x equal to 0 right here. So it's a little flat. And then it is always positive, my slope. So what that means, so basically what that means is that it's going to have to do something like this and come back down. But because it has to do that, at some point that's concave down, and then as it gets closer, it has to concave up. Do you see that? Because it has to get closer. And that's what that tells me. And then because I have to come out this way, but I need to go really tight over here, so it has to look something like this, right? At some point, that's concave up, and then has to go concave down. And then that's confirmed by my double derivative of the function. All right, guys? All right. So I think just doing the long division and studying this behavior is kind of important for those of you who had me in pre-calc honors. And I talked about that and offering how this is really offers a huge advantage, and you don't even really need calculus for that. Okay, gives you a lot of behavior on its own, really. All right, guys, let's go on to the next example. Now, before I begin, what do you suppose happens? The above is bigger than the denominator by 1, which means that when you do a long division, it's going to be a linear. Don't you think? Yeah, exactly. All right, guys, why don't you guys go ahead and try, see what you could do with it. And I'm just going to go show you the worked out problem. Okay, here we go. So the first thing I did was x-intercept with y equal to 0. It doesn't exist because the numerator is never equal to 0, right? Positive plus positive is not 0. At the very worst, that could be 0. The lowest value is 12, right? And then y-intercept is when x equal to negative 6, okay? And the vertical asymptote is when x equal to 2. And when I did the limit, right, looking for the asymptotes here, right, it come out to this, which means that as x goes to infinity this way, y goes up at an equal rate. So it's linear, right? But when I did the long division, I got this. Yeah, I got x right there. But this won't tell you how much is shifted up and down, and this one does. Okay, so I'm gonna just give me a second. I'm gonna draw a picture on this one. Let me see if I could go from corner to corner, just a tiny bit, and then let me just move it up just a bit. There you go. And then x is equal to 2. Let me do a vertical line here. These are the asymptotes, guys. Okay. And then I need to shift out the x value because my y-intercept is 2, right? So it looks kind of like this. Okay. Now, I already know where my local min and local max is, and I haven't even worked that out yet. Okay, if you look down, there's nothing else here, right? Although there's an answer that I already worked out for you. But let's examine this right here, right? That's going to be very, very, very important. Okay, so my overall behavior is this, right? As x goes to infinity, this thing goes to 0. Yes, it does, right? But let's examine that. Let's say plug in that's x is 1,000 or something, right? That's essentially 1,000. Put a million, right? That's essentially a million over negative 8. So it'll be negative 8 over million-ish, right? A little bit more than that. So it's going to be about negative 0.00000. Was that 5 zeros? and 8. So it's going to be a tiny bit below. Is that making sense? It's going to be a tiny bit below. So it's going to be like here, right? However, if you plug in a negative x, that's worth like negative million, it's positive. It means that the graph will be slightly above, over here. You know what? That's too thick. So let me thin it out a little bit. Let's just use the pink, magenta. So it's going to be like tight here. It's going to be tight over here. Okay. That is it, guys. So what does that mean? How does the graph look like, right? Let's see. Oh my gosh, because that didn't look right, and I just caught the mistake, right? I just saw it. I just saw it, guys. That was positive, and I copied down the negative and negative. That's going to be a big boo-boo. All right, guys, let's fix it. So that is a plus, and plus, and plus. That's going to be 16, okay? And let me see if I did that correctly. That's 2. Synthetic division, that's 1 multiplied by 2 is 2. That's 2, 4, 12, 16. Yep, it's 16. Yeah, because it just didn't look right. So what that tells me now is that when x is positive, now it's going to be above. Okay, so I'm going to move this graph above, and that now is going to be below. Okay, that makes more sense. Now, one of the things what else you could do is we know that this thing right here around 2, and you could try to see what happens as the limit as x approaches 2 from the positive side, guys. Just see what happens. And here, all you gotta do is just plug in some number, like 2.0001. If you do that, this value will be around 2 squared, which is about 16-ish, and the denominator is going to be a very, very positive small number, which is essentially leads to positive infinity. And that tells me that it's going to go up this way, right? And you do the same thing. Let me move things down a bit to give myself a little bit of space. There you go, right? And then let me move that over here. Okay, now let's continue. What if the x goes to 2 from the negative side of this expression? Well, the numerator, this right here, guys, is still around 4. It's like 1.99999. Will still be around 16, right? But the denominator is going to be 1.9999 minus 2, which will be negative small number. So that's going to be going to negative infinity. So that tells me that my answer is going to go down this way. And then I know that my x-intercept is, no, sorry, my y-intercept is negative 6. 1, 2, 3, 4, 5, 6. You know what? Let's call this 6, shall we? Negative 6. And what that tells me is that it will probably do something like this. Right, so get closer this way. And I haven't plugged in a value here, so that is 2. You know what we could do? Plug in full value for 4. Okay, so the p of x at 4 is 4 squared is 16 plus that is 28. And that's 4 minus 2 is 2. That would be about 14. Every 3 was about 4. So you're going to get, it's going to be like about here, right? So it's going to look something like this. Yeah. Okay, now let's get the slope, right? The slope here is positive, then becomes negative. Where does it become? At negative 2. So what that means is that around negative 2, let's say, it goes like this and then starts to come down this way. Good. So I could sort of redraw this thing, and it's going to look like that. Okay. So yeah, so the calculus portion that we're dealing with, this is the calculus portion right there, right? Will help us refine the picture, right? And that is where it goes up and down, isn't it? Up and down, so that's where the local max is. So you should do that, actually. So where's the local max, right? Happens at p of negative 2, and that would be 2, 4, 16 over negative 4 is negative 4, right? And then where's local min, right? And according to this one, is where the 6 is, right? 6 squared is 36, that's 12. That would be 48. That's 4, that would be 12. Right? Right. And then we know that when it's 4, yeah, there you go. Beautiful. So that'll tell you where the local min and max is. So this will look something like this. All right, guys? All right. You could go ahead and do the P double prime, but essentially this is the picture, right? And then going back down to, and by the way, so because of this, I was able to refine the picture on this side and this side, right? Exact to say where exactly it is the local min and the local max. However, even without that, I still could get general shape even without calculus. I already figured this out from simple logic of having this right here. And that is the big lesson today. Okay. Anyways, that's what it looks like. If you drew it proportionally and with, yeah, everything in proportions. All right, guys, let's move on to example 2. So we got this, but the difference is 2, isn't it? So it will be x squared. So as the x goes to infinity, the y will go in x squared. So it will be more of quadratic relationship as x goes to this here, right? Or here. Does that make sense? All right. Why don't you guys go ahead and see if you could do it on your own. If not, you could just wait a few seconds. All right. Okay, here we go. In this case, it was a lot easier than the question looked because maybe you figured out right away that x plus 1 divides this right away. So that's another reason why you should do a long division. But let's pretend that I didn't know that for a second. Okay. X-intercept is y equal to 0. And then I find out that that happens when x is negative 1. My y-intercept is when x equals to 0. Then my y is 1. Right? X is negative 1 here, obviously. Right? Now, what does the graph look like? Okay. Hold on a second. Hold on a second. Did I just make a boo-boo? I think I did. I think I did. Because, yes, of course I did. So this is right here, right? That's what we would have said, but just hold on to your thoughts, okay? Because that's what you would have at the beginning, right? And the vertical asymptote is what? X equal to negative 1. And to find the slant and or oblique asymptote, x goes to positive negative infinity, do all that work, and we find that the relationship is as x goes to infinity, y goes to infinity in a square relationship. So it looks more like this. But when I did a synthetic division, guys, I found out that this is the case. Oh my gosh, it cross cancels. So this is essentially then, right? What do we have? We have x plus 1 times x squared minus x plus 1 over x plus 1. It cross cancels. Then we know that this is true where x cannot be negative 1 because that is a whole. So what we should have said here was whole, right? So you do need to try to factor it out whenever possible. And then the whole will be at p of negative 1, and that would be at, let's see, and we do need to plug the negative 1 into this one, and that would be 1 plus, sorry, that'll be 1 minus minus 1 plus 1. That'll be just 3, 1 and 3. Okay. So whole will be at negative 1, 3. Okay, guys. And then I did the derivative, which gives me this. And to the left of the half, my slope was negative. To the right was positive. So local min happens at x is equal to, p of half is 3/4. Okay. All right, let's try to draw the picture. And that is the p of x, guys. Now, what I'm going to do is, if you want to call it cheating, you could do cheating, but I just want to graph by forgetting about this first. I'll shift it up later. Then we're thinking about graphing what? X times x minus 1, isn't it? So my x-intercept is 0 and 1. So that's what I have. 0 and 1. And if you plugged in a half, that would be 1/4 minus 1/2 with -4th, right? So it would be like here. And then this will, if you go up 1, it'll go up 1 over here. If you go 2, that'll be 1, 2, 3, 4 will be about here. And if you connect them, and it's going to be like this, right? But I'm going to go up this by what? 1. So the picture here will be like, I should hit that point right there. Okay, so I'm going to move this graph, this picture, by matching it right there. And that's the picture I get. All right, guys? Yeah. Anyways, there it is. And let's look at the Desmos picture. And that's pretty much what I have, right? I might have been a little bit off, but I think that was fairly accurate. If you could tell, that's about quarter below this. And that seems to confirm that right there. Okay. All right, guys. That is it. We got example 3. This will be your turn as well. This will be resemble the previous question quite a bit. And please do this. We'll discuss it in class. All right, guys. All right. Thanks for listening. And I'll talk to you guys in class. All right. If not, I'll talk to you. You'll be listening to me in the next video. Okay. Goodbye.